In 1948, John von Neumann, one of the founding figures in computer science and artificial intelligence, was giving a lecture at Princeton when an audience member interrupted him by saying, "But of course, a machine can't really think, can it?" To that, von Neumann replied, "You insist that there is something a machine cannot do. If you will tell me precisely what it is that a machine cannot do, then I can always make a machine which will do just that." Hi, I'm Dan, and in the coming weeks, I'll be teaching you the principles and skills you need in order to begin your journey into the field of machine learning. I hope to leave you with a strong foundation of knowledge, along with confidence in your own abilities that will serve you well for the rest of your career. I chose this anecdote about von Neumann because it highlights one of the biggest roadblocks in understanding AI for many people, which is thinking about computers in abstract terms. The main idea of the audience member's question was highly abstract in nature. What is a machine? What does it mean to think? These are philosophical questions that remain puzzling and controversial to this day. Yet von Neumann's reply was entirely technical. Although it may be informally worded, what he was getting at was the concept that the only operations a machine cannot perform are those that we cannot formally describe or require infinite steps to complete. This is the gist of the Church-Turing thesis, which is a formally defined mathematical conjecture. In this case, a machine refers to a construct called a Turing machine, and the concept of thinking and consciousness is avoided, instead focusing on the ability for such a machine to compute an arbitrary series of operations. Throughout this course and your career, you will come across nebulous concepts and problems that seem far too complex for you to handle. Whenever that happens, don't panic. Don't be intimidated. Define the problem formally so that you can focus on the technical, well-defined portions of it. Before we go any further, we need to learn some terminology. For starters, what is machine learning? Machine learning deals with algorithms that improve themselves. So how do we use machine learning? Well, in order to apply machine learning, we start with data. We pre-process the data into a computer-readable format, then we analyze the data. Because datasets are generally too big to analyze directly, this comes in the form of visualization. Next, after looking at the data and playing around with it for a bit, we identify the type of problem we're dealing with. Is it a regression problem, where we're looking to find relationships between variables? Is it classification, where we seek to identify a category to which an input belongs? Or is it clustering, where a set of objects is to be split into similar groups? Although this is certainly not an exhaustive list, the vast majority of problems you will come across will either be a regression, classification, or clustering problem. Finally, after we identify the problem and implement our algorithm for it, we test how good it is, and depending on how it does, either decide it's good enough and call it a day, or make some improvements to your existing implementation. This last part will depend largely on what your algorithm is going to be used for. If you need your algorithm to be extremely reliable, you may find yourself diagnosing and optimizing over and over again for months, maybe even years. Whereas if meeting a deadline is far more important than perfection, you might not spend as much time on fine-tuning. Okay, so I just threw a lot of terminology at you, but remember, don't be intimidated, don't panic, let's break it down and start at the beginning. So in this case, let's start with the data we're using. Depending on the data set you're analyzing, you'll either be dealing with discrete or continuous variables, and it's important to know the difference between the two. Discrete variables can only take on specific values. For example, the number of undergraduates at Harvard is a discrete variable. You can't have half or 1.5 or 500.01 students, it has to be an integer. Similarly, the number of defects in a batch of microchips is also a discrete variable. It doesn't make sense to say that this microchip has 0.2 or a third of a defect. It only makes sense if we say it has 1 or 2 or some whole number of defects. On the other hand, continuous variables can take on an infinite number of values on an interval. For example, time. We aren't just limited to whole numbers of seconds, we can record time to as many decimal places as we want without any problems. The same goes for distance. I can run 1 or 2 miles, but I can also run half a mile, or a third, or a tenth of a mile, or 0.111 repeating of a mile. And of course, this goes for weight as well. Note that this doesn't mean you can give continuous variables any value at all. A negative weight, for example, probably wouldn't make sense. It just means that within the interval for which they are defined, they can take on an infinite number of values in that interval. Now that we understand our data set a bit better, let's get into the machine learning. In the context of ML, the approaches we mentioned earlier deal with different types of data. Regression deals with continuous variables. Remember that regression looks for relationships between variables. I may use regression to find a relationship between height and weight, which are both continuous, but I cannot use it to find the relationship between, say, the number of undergraduates at Harvard and the number of defects in a batch of microchips. Classification and clustering are for discrete variables. Let's say I have a set of movie reviews, a discrete data set because it's made up of individual reviews. I may want to classify them into either positive or negative reviews. I might also cluster them into two groups of positive and negative reviews. However, it wouldn't try to make sense to classify or group continuous data, such as time or height. So if both classification and clustering are for discrete variables, what's the difference between them? That brings us into supervised learning and unsupervised learning. In supervised learning, the algorithm is first given a labeled training set of data. It then uses the training set to try and find a relationship between each input and the label we gave it. After the algorithm is trained, we can give it inputs without a label and have it assign a label for us. For example, if I have pictures of cats and dogs and I want to use supervised learning to identify which pictures have a cat and which pictures have a dog, I would first show my algorithm some pictures of cats and some pictures of dogs so it can learn the difference between the two. Then, after my algorithm has a good idea of what's a cat and what's a dog, we can show it a new picture and have it tell us if it's a picture of a cat or a picture of a dog. On the other hand, if we simply give our algorithm a lot of pictures of cats and dogs without telling it anything about those pictures, it would be an example of unsupervised learning. In unsupervised learning, the dataset is unlabeled, and the algorithm seeks to find structure within the data. If it's clever enough, the algorithm will identify that there are two distinct types of pictures in the data, one group of cats and one group of dogs, without any help from us at all. So to answer our original question, classification is supervised and clustering is unsupervised. Okay, I know that was a lot of information, so let's take a look at a few examples to really help solidify our understanding. Let's take a look at our first example. I visualized the data for you on the right. On the x-axis, we have husband's age, and on the y-axis, we have the age of his wife. First, is this data discrete or continuous? Well, in this case, both variables are continuous because age is just a measure of time. Second, would we want to use supervised or unsupervised learning? Well, let's look at whether or not the data is labeled. It may not be clear at first glance, but the data set we have is actually labeled. This is because for each husband's age inputted on the x-axis, we're given the correct corresponding wife's age on the y-axis. Since the data set is already labeled, we probably want to use supervised learning. And because this is supervised learning on continuous variables, this is a regression problem. Let's take a look at another example. On the left is our original dataset, and on the right is our dataset after going through a certain machine learning algorithm. The axes of these graphs are not actually labeled, so it's unclear from that alone whether or not the data is discrete or continuous. However, because there aren't any meaningful units included, we know the data isn't labeled, meaning we have to be dealing with unsupervised learning. And since we're using unsupervised learning to divide an unlabeled dataset, this has to be a clustering algorithm. Let's look at one last example. Once again, our graph doesn't have any units, so it could be either discrete or continuous variables. However, if you take a closer look, you'll see that the legend of the graph on the top left give each data point a different color corresponding to 0, 1, and 2. In other words, this dataset is labeled, meaning we probably want to use supervised learning. And by looking at this nice graph we have, we can see that these three labeled sets of points each clump up into separate groups. Based on this analysis, we would most likely want to approach this as a classification problem. So we've talked a lot about algorithms, but you'll have to implement them somehow. In this course, we'll be using the programming language Python and the Jupyter Notebook application to do our machine learning. In this course, we don't expect you to have any prior programming experience. That's why we chose Python, because it's an easy to learn and concise and readable language. Additionally, there's tons of resources available in case you run into problems. Python is also a very versatile language that you can use for tons of applications later on in your career, even if you decide not to go into machine learning. Here's a quick graph showing just how popular Python is in machine learning and data science. If you decide to go into this field, there's a good chance you'll be using Python for a living. The reasons we chose for using the Jupyter Notebook application is because it's easy to use, it's easy to share, and it's very intuitive. These all make it very beginner-friendly. It also supports a lot of languages, so not just Python, but also other popular languages like R and Julia, which are very popular in machine learning and data science as well. Python is great, but as you learn more languages and improve your skill set moving on in your career, you'll want to make sure that your IDE scales with it as well, and Jupyter can provide that. Today, we learned a basic problem-solving approach for machine learning. We start by restating the problem, then we analyze the dataset, and from there, select the best approach to take. After implementing the algorithm, we identify flaws and improve our algorithm until it performs at the level we need it to. Additionally, we outlined and looked at examples for the three main types of problems we may encounter. Regression, a supervised approach in which we look for relationships between continuous variables. Classification, a supervised approach in which we train our algorithm to assign labels to inputs. And clustering, an unsupervised approach where our algorithm looks for structure within unlabeled, discrete data. For next week, install Jupyter Notebook and make sure it works by printing Hello World. An installation guide, additional questions to test your understanding, as well as today's slides can be found at the link in the description. Hope you learned something, and I'll see you again soon.